I was reading through the source material for today's deep dive early this morning. Specifically that seminal paper from Google, the sculling line.
With the technical debt paper. A classic.
And I came across this one diagram that, I have to be honest, it just stopped me in my tracks. I actually had to put my coffee down.
That is a serious reaction for a Tuesday morning. Usually those papers are more likely to, put you to sleep than wake you up.
Yeah.
What was it?
It was this visual of a whole machine learning system, and you look at it, and there's this tiny, tiny little black box right in the middle.
Right.
And it's labeled ML code. And I mean, it is minuscule. It looks like a postage stamp on a giant billboard.
And everything else around it?
It's just completely surrounded by this sprawling maze of other boxes. You've got configuration, data collection, verification, serving, monitoring, resource management. It just goes on and on.
Yes. The famous hidden technical debt paper. It's a real visual punch in the gut, isn't it? Especially for anyone who thinks their job is just tweaking hyperparameters or, playing with neural networks.
Well, that's the thing. The statistic that jumped out at me from the text was that building the actual AI model, the algorithm, the math, the thing we all think of as the magic, is only about 20%.
And that's being generous.
Maybe even 5%, it said, of the actual work required to make a system usable.
That sounds about right. I mean, for a really mature system, the actual model code itself might be the smallest component just by line count. It's wild.
But think about that for a second. We spend all our time talking about the neural networks, the transformers, ChatGPT. We talk about the brains of the operation. But this deep dive isn't really about the brain. It's about everything else.
It is. And to use an analogy, imagine you've spent years, designing the absolute perfect internal combustion engine. It's a Ferrari engine. A masterpiece of thermodynamics. It's powerful, it's efficient, it purrs like a kitten, but you have no chassis.
Right.
You have no wheels, no steering column, no brakes, no gas tank, and importantly, no road to drive on.
So what I have is a very loud, very expensive paperweight sitting on my garage floor.
Exactly. You have an engine sitting on concrete.
Yeah.
It might run perfectly in isolation. You can rev it up, listen to it, but it's not going to take you to the grocery store.
And it's certainly not winning any Formula One races.
Not a chance.
Yeah.
So today we are not talking about the engine. We're talking about the car. We're talking about the whole infrastructure that's required to take that model file from some data scientist's laptop and turn it into a global service that runs 24 hours a day, 7 days a week without ever crashing.
We are diving deep into the world of MLOps, machine learning operations. And our mission today is really to uncover that hidden 80, maybe 95%, the plumbing, if you will, that makes all the magic actually work.
And we should probably set the scope here, because this is a massive field and we could easily get lost in the weeds.
Good point.
We're not talking about how to train the algorithm today. We aren't discussing how to select hyperparameters or design network layers. We're making a big assumption.
Which is?
We're assuming you have the model, the binary file is ready, the science experiment part is over.
Okay.
Today is about three things, and three things only: serving, scaling, and surviving.
I like that framework. Serving, scaling, and surviving. It's got a nice ring to it.
So we're going to look at the roadmap. First up is the data. How do we feed the model information in real time without accidentally cheating? That gets us into the whole architecture of feature stores.
Okay, data first.
Second, the service. How do you tune a static file into, a website API that can handle millions of requests a second? That's all about serving engines. And finally, the scale. How do you manage traffic and costs when 1 million people show up at your digital doorstep at once? That leads us into the sort of city planning world of Kubernetes and the wallet watching world of FinOps.
And I'll just tease this for everyone listening right now. There is a concept coming up that the source material calls time travel.
Yes. It sounds like something out of science fiction, but it is a very, very real and expensive engineering problem.
And apparently it's a massive financial risk in data science. So if you're listening, you want to stick around for that, because I promise by the end of this hour, you are going to look at your favorite apps, your Netflix, your banking app, Uber completely differently.
You'll see the invisible machinery.
Exactly. The invisible machinery that's keeping them all alive.
Shall we open the hood then?
Let's do it. So let's start with data, but not just data as this big abstract cloud. The sources get very specific about a piece of architecture called the feature store, and they frame it as the solution to a problem called training serving skew. Now, can we unpack that term? Because skew sounds like a minor statistical nuance, but the source material treats it like it's a five-alarm fire.
It can be a catastrophe. It absolutely can. It is the silent killer of AI projects.
A silent killer. Wow.
Yeah. To understand it, you have to understand that data scientists and software engineers, they basically live in two different worlds. There's the world of the lab and there's the world of the wild.
Okay, let's break down the lab first. What does life look like in the lab?
In the lab or the training phase, you're always looking backward in time. You're working with historical data.
Right.
You have this massive data set of everything that's happened in the past year, 5 years, whatever. You're probably using tools like SQL or Python libraries like Pandas.
A standard data science toolkit.
Exactly. And you're processing things in these big batches. It's slow, it's very thorough, and you can take your time scanning millions, even billions of rows to find interesting patterns.
Right. It's like being a historian in a library. You've got all the books, you can cross-reference everything, and nobody's rushing you. If a query takes 10 minutes to run, you go get a coffee. No big deal.
Precisely. But then you deploy the model. Now you are in the wild,
Out of the library.
out of the library and into the jungle. This is real-time inference. This is when a user clicks a buy button on a website or swipes their credit card at a terminal.
The moment of truth.
You don't have hours to scan a database. You don't even have seconds. You have milliseconds. And the code is often different too. It might be in Java or C++ instead of Python because the production engineers need it to be absolutely lightning fast.
So you've immediately got a speed mismatch and probably a language mismatch.
And that is what leads to the skew. Imagine you have a feature in your model. Let's call it average user spend.
Yeah, okay.
In the lab, you calculated that using some complex SQL query over 5 years of historical data. But in the wild, the app needs to calculate that same number right now at the exact moment the user's checking out. If the logic to calculate average user spend in the live Java application differs even by a fraction of a percent from the logic you used in your historical SQL query,
The model just used. What? It fails.
it fails.
Mhm.
Or worse, it doesn't fail, just gives you garbage predictions.
Mhm.
The model was trained to expect a very specific kind of input. If you give it something even slightly different because your live calculation logic is off,
Like what? What's an example?
well, maybe the SQL query that you use for training excluded returned items, but the live Java code for some reason doesn't. Or the SQL query was time zone aware and the live code isn't. Tiny things.
I see. So the numbers look almost the same, but they're not identical.
And the model's predictions become unreliable.
Yeah.
That is training serving skew. It's a subtle but deadly problem.
It's like practicing for a play using one version of the script, and then on opening night, all the other actors are using a slightly different version.
That's a great analogy.
You're going to miss your cues, you're going to say the wrong lines, the whole thing falls apart.
Exactly. So enter the feature store. This is designed to be the single source of truth,
The one script for everyone.
the one script. It ensures that the definition of a feature, like our average user spend, is written once and is identical in both the lab and in the wild. You define the logic once, and the feature store handles delivering that value to both the training environment and the production environment.
Okay, so the source material breaks this down into two planes. It talks about an offline store and an online store. This felt like a really crucial distinction, almost like the system has a split brain.
It is the architectural heart of the entire system. It's a brilliant solution. Let's look at the offline store first.
Okay.
This is your library, to use your analogy from earlier. The archive. This is built on technologies like Snowflake, BigQuery, or sometimes just massive S3 buckets filled with Parquet files.
I saw that term, Parquet files. Can you just quickly explain what that is? Is it just a file format?
Yeah, it's a column-oriented storage format. So instead of storing data row by row like a traditional database, it stores it column by column.
And why is that better?
It's incredibly efficient for compression and for heavy analytics. It lets you scan billions of rows of just the columns you need very, very quickly. It's perfect for when you're doing research or generating these huge training sets.
So this is the deep storage, the archive, where all the history lives.
Yes. It stores months or even years of historical feature values. Its primary goal is high throughput. It needs to be able to generate massive training data sets.
Yeah.
It doesn't really care if a query takes 10 minutes to run as long as it gets all the historical data with perfect accuracy.
Okay. But we obviously can't use that when I'm swiping my credit card at a store.
No way.
I can't wait 10 minutes for a fraud detection model to run while the system unpacks a terabyte of Parquet files.
Correct. And that is precisely why we have the online store.
Yeah.
This uses a completely different set of technologies. We're talking key value stores like Redis, DynamoDB, or Cassandra.
And the goal here is the opposite, right? It's not throughput, it's...
Speed. Pure, unadulterated speed. Low latency. We're talking single-digit milliseconds.
Wow.
The online store doesn't keep the history. It's designed to only keep the latest value of any feature. So if you're user 123, the online store just knows. User 123, current status, active, last location, New York, average spend, $50. That's it.
Yeah.
It has no idea what you did last year. It just knows what you look like right now.
It's like a sticky note on your monitor.
That is the perfect way to visualize it. And steal that.
So the offline store is the dusty archives in the basement where you do all your deep research. And the online store is the sticky note on the monitor with just the 3 facts you need to know for the meeting that's happening in 10 seconds.
Exactly. And the magic of the feature store is that it manages the synchronization between them, so the number on that sticky note always matches the latest research from the basement. No skew.
Okay, this is making sense. Now we have to get to the time travel part. The source calls this point-in-time correctness, which sounds very academic, but the example they gave about fraud detection really clarified the stakes for me.
This is one of those concepts that gives data engineers genuine nightmares. It's all about preventing something called data leakage.
Data leakage. It sounds like a plumbing problem, but in the world of AI, it's actually about cheating, isn't it?
It is cheating, and it's almost always accidental. Let's walk through the scenario so you can really picture this. Imagine we're building a model to detect credit card fraud.
Okay.
We have a specific event in our training data. A fraudulent transaction happened on Monday at exactly 10:00 a.m.
Monday, 10:00 a.m. The bad guy swipes the stolen card. Got it.
Now, we want to train our model to recognize this pattern. One of the features we think might be useful is, say, average daily transactions for that user. We want the model to know what the user's spending behavior looked like at that exact moment in time.
Right. So we look at the user's data for that Monday.
But here's the trap. Suppose the thief goes on a little shopping spree. At 10:05 a.m., 5 minutes after the initial fraudulent event, they use the card to buy a luxury boat, a massive transaction.
Okay, I think I see where this is going. If we just ask the database for all of Monday's transactions,
That boat purchase is going to be in there. If we're not careful, when we go to calculate the average daily transactions for Monday to train our model on the 10:00 a.m. event, we might accidentally include that 10:05 a.m. boat purchase in our calculation.
so the model literally sees into the future.
Exactly. It's looking at the event from 10:00 a.m., but it has information from 10:05 a.m. It knows that the user's spending spiked that day, so it very easily predicts the fraud. It says, oh, well, obviously this is fraud. Look at that huge boat purchase.
But in the real world, at 10 a.m., the boat hasn't been bought yet. The system wouldn't have that information.
Precisely. So you end up training a model that gets like 100% accuracy in the lab because you've accidentally given it a crystal ball.
But then when you put it in the real world, it fails miserably because it can't actually see the future.
That is data leakage in a nutshell. The model learned a correlation that doesn't exist in reality. And fixing it requires this time travel, or what the techies call an ASO join.
ASOF, standing for as of.
Right. You need the feature store to go back in time to Monday at 10:00 a.m. and reconstruct the state of the world exactly as it looked at that second. It has to ignore everything that happened at 10:00 and later.
And the source mentioned that writing the SQL code to do this manually involves these complex window functions and is, and I'm quoting, a nightmare.
It is an absolute nightmare. It is so incredibly prone to human error. One tiny typo in your timestamp logic, one off by one error, and you've introduced leakage into your entire training set without even knowing it.
And you'd never catch it in testing.
You'd never catch it. Your model will look amazing. That's why these dedicated feature store tools like Feast or Tecton are so valuable. They handle this time travel logic for you automatically. They guarantee that for every training label at a specific timestamp, you only retrieve the feature values that were valid at that exact moment. They keep you honest.
So the feature store isn't just a fancy bucket for data. It's a time machine that enforces the rules and keeps us from cheating.
That's a great way to summarize it. It ensures that the model you build in the lab is actually capable of surviving in the wild.
All right, so that's a lot on data. I feel like we have our data house in order. We've got our time machine. We've trained a model that doesn't cheat. Now we have this binary file. It's sitting on a laptop.
The science experiment is complete.
Yes. But now we need to get it out to the world. We need to, as you said, serve it.
Yes. And this is another one of those steps where many people assume it's simple. Just put it on a server and expose an API.
Yeah.
But you can't just email a binary file to your users. You need a proper serving engine.
The source compared choosing a serving engine to choosing a vehicle. You have to pick the right one for the job. And it seems like we have three main candidates here: TensorFlow Serving, NVIDIA Triton, and TorchServe.
That's right.
Let's break them down. First up, TensorFlow Serving, or TFS.
TFS is the heavy-duty truck. It is the industry standard for productionizing TensorFlow models. It's written in C++ec, which means it is incredibly fast and highly optimized. It has been battle-tested by Google at massive scale for years.
The source mentions it supports something called hot swapping. Why is that such a big deal in production?
Think about uptime. Think about never going down. You're Amazon or Netflix. You have a critical recommendation model running.
Right.
You want to update it to version 2. If you have to shut down the server, replace the model file, and then restart it, that means downtime, even for a few seconds. That means dropped connections, failed requests.
Which is a complete no-go for a company of that size.
Exactly.
Yeah.
TFS allows you to load version 2 into memory while version 1 is still happily answering requests. It waits until version 2 is fully loaded and healthy, and then it seamlessly switches the traffic over without dropping a single packet. It's incredibly robust.
But there's a downside. The source calls it rigid. What does that mean in practice?
It's very rigid. Because it's this high-performance compiled C++ application, it's very difficult to inject custom logic into the request flow.
Give me an example.
Let's say you have an image classification model. Before the model sees the image, you want to take the raw image, resize it, maybe crop it, and turn it to black and white.
Some pre-processing steps?
Right. In TFS, that's actually quite difficult to do inside the server. You have to configure everything in these complex files called protobufs, or you have to do all that pre-processing in a separate service before you even call TFS. It's not very friendly if you want to tinker.
Okay, so TFS is the rigid, reliable corporate standard, the big truck. What about NVIDIA Triton? The source calls this one the Swiss Army knife.
Triton is fascinating because it's completely agnostic. It doesn't care what framework you use to build your model.
Really?
Yeah. You have a TensorFlow model? Fine. A PyTorch model? Fine. ONNX TensorT? Fine. It will run all of them simultaneously on the same server.
That seems like a huge advantage for a big company that might have different teams using different tools.
It is. It's a huge operational win. But its real superpower is GPU utilization. GPUs are incredibly expensive assets. You do not want them sitting idle.
You want them working hard for their money.
You want them sweating. Triton's incredible at managing the memory and compute of the GPU to squeeze every last ounce of performance out of it. It supports something called concurrent model execution.
Meaning it can run different models at the exact same time on a single graphics card.
Exactly. It intelligently schedules the work so that every core of that GPU is busy. It's the ultimate high-performance multitasker.
And then we have our third option, TorchServe. This one is described as being deeply Pythonic.
TorchServe is for the developers who really love to write code. It was developed jointly by AWS and Meta. If you are a Python native, this environment feels like home.
So remember that image resizing problem we talked about with TFS?
The custom logic, yeah.
How does TorchServe handle that?
In TorchServe, it's trivial. You just write a Python function. They call it a handler. You can write code to unzip a file, transform the data any way you want, run the prediction, and then format the output as a clean JSON response. It's incredibly flexible.
But there's always a trade-off, right? What's the catch here?
The catch is raw speed. Python is an interpreted language, and it's just fundamentally slower than compiled C++ pure.
Yeah.
You have things like the global interpreter lock in Python that can become a bottleneck. So, as a general rule, TorchServe will have lower raw throughput than Triton or TFS.
So you're trading that raw speed for ease of development and flexibility.
That's the choice you're making. Do you need the absolute maximum performance, or do you need the ability to write custom Python logic easily?
So to recap, TFS for raw C++ speed and stability. Triton for flexibility across different frameworks and squeezing every drop of power from your GPU. And TorchServe if your workflow requires custom Python logic and you value ease of use.
That's the landscape in a nutshell.
Now, regardless of which of these engines you pick, there's a mechanism the source dove into that I found really, really counterintuitive at first. It's called batching. Specifically, inter-request batching.
Ah, yes. This is the secret sauce of high-throughput model serving. It's magic.
But the source says that to do this, the server actually waits for requests to come in. That sounds completely wrong. If I want a fast app, why on earth would I want the server to wait?
It's all about the physics of the hardware we're using. We're running these models on GPU's graphics processing units.
Right.
These chips were originally designed for video games, for rendering triangles.
Mm.
They are designed for massive parallel processing. They are like giant calculators that can do thousands and thousands of math problems all at once. They love working with matrices.
Okay, I'm with you so far.
And think about it this way.
Mm.
If I give a GPU one simple math problem to solve, it takes, let's just say, 10 milliseconds.
Right.
Now, if I give that same GPU 32 of those math problems at the exact same time bundled together, it still takes
Yeah.
roughly 10 milliseconds.
Wait, really? It doesn't take 32 times longer.
No. That is the magic of parallel processing. The main overhead is in moving the data to and from the chip and triggering the computation. Once the chip is fired up, doing the math on a matrix of size 1 versus a matrix of size 32 is almost a negligible time difference.
So if you just send requests to the GPU one by one as they arrive, you're massively wasting the GPU's potential power.
Exactly. You're driving a massive 50-seater bus with only one passenger on it. It's incredibly inefficient. So inter-request batching is like the bus driver waiting at the bus stop for a minute.
Hold on, don't leave yet. Let's see if anyone else is coming.
Precisely. The serving engine waits a tiny fraction of a time, maybe just 2 or 3 milliseconds, it's configurable,
Yeah.
to collect incoming requests from different users. It then stacks them up into a single batch. It fills the bus and sends them all to the GPU at once.
So for me as the individual user, my request waits an extra 3 milliseconds.
Which is completely imperceptible to a human. You will never, ever notice that delay.
But for the system owner, the person paying the cloud bill,
The total number of requests per second that the system can handle, the RPS, goes through the roof. It can be a jump of 10x, 50x, even 100x. You are serving way more people with the exact same hardware.
that is a brilliant trade-off. A tiny, imperceptible delay for the individual results in a massive efficiency gain for the crowd.
It is the very definition of efficiency at scale. It's one of the most important optimizations in all of MLOps.
Okay, so we've chosen our engine, we've cleverly set up batching, we're ready to deploy and go live. But then the source material takes a bit of a dark turn here. It starts talking about risk and blast radius.
Because deployment is terrifying. It's
Really?
where careers go to die.
The source says, and I quote, "Deploying a new model feels scary. What if it's wrong?" And I totally get that. If you change the algorithm for a recommendation engine and suddenly it starts recommending horror movies to toddlers,
You've got a PR nightmare on your hands.
or even worse, if you deploy a new fraud model that incorrectly blocks everyone's credit cards on Black Friday.
You could lose millions of dollars in minutes. And see, this is the key difference. Software bugs usually cause things to crash. AI bugs cause things to make wrong decisions. And wrong decisions are so much harder to spot than a server crash. That is why we need specific deployment patterns. These are our safety nets.
The first one the source mentions is the sidecar pattern. This immediately made me think of a motorcycle.
It's a great visual and it's very apt. In the world of Kubernetes, a pod is the basic unit that wraps your application container.
The house, from our later analogy.
Exactly, the house. Usually you put your model server in a container inside that pod, but you don't want your brilliant, complex model code to also have to worry about things like SSL certificates or logging or authentication.
Right, the model should just be focused on doing math. It shouldn't have to be a security expert or a logging framework.
Exactly. So you add a second separate container to the same pod, the sidecar. This might be a lightweight web server like NGINX or Envoy or maybe an Oath proxy. It sits right next to the model container.
Like a Copilot or bodyguard.
All the external traffic hits the sidecar first. The sidecar handles all the security, the logging, all that boring infrastructure stuff, and then it passes a clean, verified request to the model on localhost. It completely decouples the infrastructure concerns from the intelligence concerns.
That makes a ton of sense. Keep the genius focused on the math. Let the bodyguard handle the door.
Correct. Now, once you have that clean structure, how do you actually release a new version of the model? This brings us to my favorite pattern, shadow deployment. It's also known as a dark launch.
Dark launch. Sounds very spy movie.
It is, and it's my favorite because it is essentially zero risk.
How can it possibly be zero risk? You're still putting new code into production.
But the user never sees the result. Here's how it works. You have version 1, your current trusted model, serving all the live traffic. You then deploy version 2 alongside it.
Okay.
Then at the network level, maybe in your load balancer, you duplicate all the incoming production traffic. Every single request gets sent to both version 1 and version 2 simultaneously.
Okay, so both models are running and making predictions.
Both models are running, but, and this is the key, The system is configured to only return version 1's answer to the user. Version 2 makes its prediction, but that prediction goes into the void.
It's basically talking to itself in a locked room.
It is,
Yeah.
but we are recording its answers. And more importantly, we're monitoring its health. Does version 2 crash under load? Is it slower than version 1? Does it throw a bunch of errors? We can test it under full real-world production load without a single user ever knowing it exists.
That is absolutely brilliant. You get to verify that the new engine doesn't explode when you take it up to 120 miles per hour before you actually put a real driver in the car.
Exactly. And you can compare the predictions. If version 1 says not fraud and version 2 says fraud, you can log that discrepancy and have a data scientist investigate why. It's an incredible safety net.
So once you're happy with the shadow model's performance, what's next?
Then you might move to the next pattern, the canary deployment.
Like the classic canary in the coal mine.
The very same concept. You don't just flip a switch and send 100% of traffic to the new model. That's too risky. Instead, you shift the traffic gradually. You start by sending just 1% of your users to the new model.
Just a tiny slice of the pie.
A tiny slice. If the new model is terrible, or if it has some catastrophic bug, only 1% of your users are annoyed, not everybody. You dramatically limit the blast radius of the failure.
And how do you pick that 1%? Is it random?
It's usually deterministic. You might use a hash of the user ID. For example, if your user ID ends in the number 7, you get sent to the canary. This creates what are called sticky sessions, so the same user doesn't get bounced back and forth between the old and new versions, which would be a really confusing user experience.
And if the canary survives, if all the metrics for that 1% of users look good,
You slowly dial it up. You go from 1% to 10%, then to 50%, and finally to 100%. It's all about building confidence. You don't guess, you verify at every step. In MLOps, paranoia is a virtue. And these patterns, sidecar, shadow, canary, are just structured paranoia.
structured paranoia. I love that. Okay, so this is all great, but it feels like we're assuming there's some underlying system managing all these containers and traffic routing. And that brings us to the backbone of all of this. The source material calls Kubernetes the operating system of the cloud.
KACE. You really can't avoid it these days if you're working in tech.
It seems like you can't talk about modern infrastructure without talking about Kubernetes, but it is notoriously complex. The source breaks it down into these core components: pods, nodes, services, deployments. Can we simplify this hierarchy? I feel like I need a map to understand it.
Let's imagine we're building a city. Let's be city planners for a minute.
Okay, SimCity style. I'm ready.
The most fundamental thing you need is land. That is the node. In the cloud, the node is the actual virtual machine, the server itself, like an Amazon EC2 instance. It provides the raw resources, CPU and RAM. It's the soil and the space.
The node is the land. Got it. Simple enough.
On that land, you build a house. That is the pod. A pod is the smallest deployable unit in Kubernetes. Your actual model application in its container lives inside the house. A single node can hold many pods, just like a large plot of land can have many houses on it.
Okay, so the model lives in the pod, which is the house, which sits on the node, which is the land.
Perfect. Now, you need a town planner. That is the deployment. You tell the deployment, I want 3 identical houses to be standing at all times. If one house burns down, meaning the application crashes, the deployment automatically notices and immediately builds a new identical one to replace it. It manages the desired state.
So the deployment is like the city government or the insurance policy. It makes sure we always have enough housing.
And finally, you need a road system and an address book. That is the service. Pods are ephemeral. They come and go. They get destroyed and rebuilt all the time. Every time a new one is built, it gets a new internal IP address. You can't rely on their direct address.
It's like the house numbers keep changing.
Exactly. So the service provides a single, stable address, like a permanent street address or a URL, that intelligently routes traffic to whichever healthy houses are currently standing. It acts as the internal load balancer so that requests can always find a way to the right pods.
Okay, that city planning analogy actually helps a lot.
Yeah.
Land is the node, house is the pod, town planner is the deployment, and the road system is the service.
There you go.
Now, the most impressive trick that Kubernetes pulls off, according to the source, is auto-scaling. This is how a system like Netflix or Twitter handles a sudden viral spike.
Yes. And it's important to understand that there's a hierarchy here too. Scaling actually happens at 2 different levels, and people often confuse them.
Okay.
First, we have the HPA, the horizontal pod autoscaler.
Horizontal, meaning we add more things next to each other, more houses on our land.
Exactly. This scales the number of pods. Let's say your model is getting hammered with traffic.
Oop.
The CPU usage on your existing pods spikes to 90%. The HPA is constantly watching that metric, and it notices this. It says, we need more houses to handle all these people. So it automatically spins up more replicas of your model pod to share the load.
And this happens pretty fast.
Very fast. We're talking seconds or maybe a minute. It's just starting a software process. It's like putting up a prefab house. Quick and easy.
But what happens if you run out of land? What if all your nodes are full?
Exactly. That's the next level of the problem.
Sure.
What if you filled up all your existing nodes with pods? The HPA tries to build another house, but the underlying node says, sorry, no room. All my CPU and RAM are allocated. The new pod goes into a pending state. It's basically homeless.
And this is where the cluster autoscaler comes in.
This is the second, slower level of scaling. The cluster autoscaler is watching for homeless pods. It sees these pending pods and says, uh-oh, we need more land. It then makes an API call to Amazon or Google or Microsoft and requests a brand new virtual machine, a whole new node.
And this, I'm guessing, is much slower.
Much, much slower. Spinning up a new physical or virtual machine takes time. The cloud provider has to provision it, boot the operating system. It can take anywhere from 2 to 5 minutes. So you have this elegant dance. The HPA reacts quickly to traffic spikes by adding pods, and the cluster autoscaler reacts slowly to resource limits by adding nodes.
The source also mentions a concept that seems very trendy right now called scale to zero. This is the serverless dream, isn't it?
It is. Tools built on top of Kubernetes like Kserve or Native allow for this. The idea is that if no one is using your application, say, at 3:00 a.m. on a Sunday, the number of pods can drop all the way down to 0.
And you're paying for nothing because no compute is running.
Exactly. From a cost perspective, it's amazing.
That sounds perfect for my wallet. Why doesn't every single person do this for every application?
It's great for the wallet, but it is terrible for the first user who wakes up at 3:01 a.m. and wants to use your app.
Why? What happens to them?
They get hit with a cold start problem. Since there are 0 pods running, when that first request comes in, the whole system has to scramble. It has to tell the cluster autoscaler to maybe start a node. Then it has to schedule the pod, pull the container image from a registry, start the application, and then the application has to load that multi-gigabyte model file into memory.
So that first user is just staring at a loading spinner for 5, maybe 10 seconds.
Or longer, exactly. And in today's world, that's an eternity. So it's a fundamental trade-off. Do you want instant, low-latency responses for everyone, which costs money to keep servers warm and waiting? Or do you want the cheapest possible bill, which introduces this painful lag for the first user after a quiet period?
That is a perfect transition to our final big section, observability and FinOps, which is really about monitoring and money.
The two things that keep the business running and the engineers employed.
And the source makes a really strong point that standard monitoring, just, checking, is the server up or what's the latency? It's completely insufficient for AI systems.
Totally.
You can have a server that is perfectly healthy, it's returning a status 200 OK on every request, but the AI itself is completely and utterly broken.
Because AI fails silently. If a traditional web server breaks, it usually crashes or it returns an obvious error code like a 500 or a 404. It screams, I'm broken. But if an AI model breaks, it just gives you a wrong answer very confidently. It doesn't throw an error. It just quietly starts making bad decisions.
And this brings us back to that concept of drift. We teased it in the intro. Let's dig in.
There are 2 main types you have to watch for. The first is data drift. This is when the world changes. The inputs to your model change. A classic example is, imagine you trained a model to predict housing prices using data from 2019.
And then the year 2020 happened.
Exactly. The pandemic hit. The entire economy changed. The inputs your model relies on, interest rates, unemployment figures, remote work trends, they all shifted completely. The distribution of the data in the real world today looks nothing like the data you're trained on. That is data drift.
And how do you even measure that?
You use statistical metrics, things like KL divergence or population stability index. They're basically mathematical ways of asking, how different is the shape and distribution of today's data compared to the shape of the data from our training set? And you set alerts on that.
And the second type is prediction drift.
Right. This focuses on the output of the model, not the input. Let's go back to our fraud model. Let's say historically, it flags about 1% of all transactions as potentially fraudulent.
Okay, that's its baseline.
That's its baseline. Suddenly, on Tuesday afternoon, it starts flagging 50% of all transactions as fraud.
Whoa. Something is clearly very, very wrong.
The server is fine. The code hasn't changed. But the model's behavior has shifted radically. You need alerts for this. You need a dashboard that flashes red and screams at you when the prediction distribution shifts dramatically from its historical norm.
The source also mentioned a third problem here, ground truth lag. This one felt particularly tricky. It's the delay in knowing if you were actually right.
This is the fundamental painful problem of applying AI in the real world. In a lab, you have all the labels. You know the answers immediately. In the real world, well, let's say you have a model that predicts a user will default on their loan.
You're not going to know if you were right for months or, in some cases, years.
Exactly. So how can you monitor the accuracy of your model today? The honest answer is you can't. You have to use proxies.
Proxies, meaning indirect signals.
Indirect, weaker signals that are available much sooner. For a Netflix recommendation system, the true ground truth is, did the user enjoy that movie? But you'll never really know that. The proxy is, did they click on it, or did they watch more than 5 minutes of it?
Or for the loan example.
For the loan, maybe the proxy is, did they miss their very first payment? It's not a perfect signal, but it's something you can measure this month, not 2 years from now. You have to get creative because the ground truth almost always arrives late to the party. You have to rely on these weak signals to know if your model is flying blind.
Okay, that's monitoring. Finally, let's talk about the bill. FinOps, financial operations, because apparently machine learning is really expensive.
It's incredibly compute hungry. For many tech companies, the cloud bill is the second biggest expense on the books, right after employee salaries. And GPUs are the single most expensive type of instance you could possibly rent.
The source highlights something called spot instances as a major way to save money. But these sound like a bit of a gamble.
They are a gamble, but a calculated one. Spot instances are essentially the unsold inventory of the cloud. AWS, Google, Azure, they have these massive data centers. They can't just turn the servers off at night. So if they have servers sitting idle with no one using them, they'll sell you that capacity at up to a 90% discount just to get some money for it rather than nothing.
A 90% discount is a huge deal. What is the catch? It sounds too good to be true.
The catch is called preemption. If a full-paying customer comes along and needs that server you're using, the cloud provider takes it back from you.
Just like that, they kick you off.
You get a 2-minute warning, a little signal that says, you are being evicted, get out.
Wow. 2 minutes. So you definitely can't run a critical database on a machine like that.
Absolutely not. But you can run certain kinds of workloads on them. Batch training is a perfect example, as long as you use checkpointing.
Meaning you save your progress frequently.
Right. If your model training job saves its weights to cloud storage every 10 minutes, and then your spot instance gets taken away, you just lost 10 minutes of work. You can have an automated system that just picks up the job on a new spot instance from the last checkpoint. You lose a little time, but you save 90% of the cost.
Or the source mentioned using them for stateless inference.
Right. If you have a cluster of 100 servers all doing inference behind a load balancer, and maybe 5 of them are cheap spot instances that suddenly vanish, who cares? The load balancer just stops sending traffic to them and routes it to the other 95 stable machines. It's about engineering your architecture to be resilient to this kind of failure in exchange for a massive cost saving.
And the final concept in FinOps that the source discussed was unit economics. This means moving away from just looking at the total bill at the end of the month.
This is a sign of a really mature MLOps organization. You don't just look at the total and say, we spent $50,000 this month. You break it down. You calculate your cost per inference. How much does it cost us in fractions of a cent to make one single prediction? Is it 0.001? Is it $0.15?
Or the cost per training run.
Exactly. If your data science team says we have a new model that's 0.1% more accurate, the FinOps question is, okay, but it requires a GPU that's twice as expensive and it costs $10,000 to retrain every week. Is that tiny accuracy improvement actually worth the cost?
That's a business decision, not just an engineering or a science decision.
And that is the absolute core of MLOps. It bridges that gap between the cool science project in a notebook and a sustainable, profitable business function. It translates abstract concepts like accuracy into the language the business understands, dollars and cents.
We have covered a massive amount of ground today. I mean, from the feature store acting as a time machine to prevent this skew, to the serving engines acting as specialized vehicles for our models, all the way to the structured paranoia of deployment patterns, the city building of Kubernetes, and finally, the hard-nosed financial strategy of FinOps.
It is a lot, but it brings us right back to that first statistic we talked about. This is the 80 or 90%.
Yeah.
This is the chassis, the wheels, the steering, the roads, the fuel system. This is the stuff that makes the engine useful.
It really, really makes you appreciate the insane complexity that's hidden behind a simple product recommendation or a notification on your phone.
It does.
Okay.
It's the infrastructure that separates the science experiments that stay on a laptop from the products that actually work for millions of people
Yeah.
and change the world.
Before we go, I want to leave our listener with one final thought to mull over. We talked about that cold start problem,
Yes.
how we often keep servers running 24/7, burning electricity, just so that we don't have to wait an extra 3 seconds for an app to load.
It's a provocative point to end on for sure.
It really is. When an app lags, our immediate reaction is annoyance, right? We tap the screen, we complain about the bad connection. But that lag might not be a bad connection at all. It might be a Kubernetes cluster waking up from a deep sleep just for you.
Mm-hmm.
The alternative, this world of always-on instant AI requires a massive, constant expenditure of energy. Servers spinning in data centers, consuming electricity, generating heat, costing huge amounts of money, often doing absolutely nothing, just waiting for us.
It really raises the question, is our own impatience the single biggest driver of the carbon footprint of the AI industry?
It's something to think about the next time you're staring at a loading spinner. Maybe just give it those extra few seconds. You might be saving a tiny piece of the planet.
I will try to remember that next time I'm waiting for a movie recommendation to load.
And to our listeners, maybe look for the drift in your own life. Is
Yeah.
your mental model of the world still based on data you collected back in 2019? Maybe it's time to retrain. Thanks for listening to this deep dive.
See you next time.